Second part of this section, and this time we're going to talk about the kernel. So let's read the definition first. The kernel of a linear transformation T from Rm to Rn consists of all the solutions to the equation T of x equals 0, and it is written Ker of T, K-E-R of T. So this is what corresponds to looking for the zeros of a function. We are looking for the x values in a function such that f of x equals 0, and here it's t of x equals 0. So we are going to try to solve the equation a of x equals 0 when we look for vectors in the kernel. Now notice how just like the zeros of a function are x values, the kernel of a transformation is going to be a subspace that belongs to the original space. So it's a subspace of Rm, whereas the image is a subspace of Rn. It's written here, Ker T is a subset or subspace of the original space, and then the image is a subspace or subset of the target space. So let's think geometrically first. What is the kernel of the linear transformation T of x equals x1, x2, 0? So what we are trying to answer is what vectors x1, x2, x3 are going to give me 0, 0, 0. And the answer is any vector where the first two components are zeros are going to be part of the kernel. It does not matter what x3 is. So for example, the vector 0, 0, 7 is going to go to 0, 0, 0. So all vectors of the form 0, 0, c, or all vectors of the form c times 0, 0, 1 are what the kernel is composed of. And we would write this, the kernel of T is the span of vector 0, 0, 1. So the span again is like all the linear combinations, but here we have just one vector, so all we can do with it is multiply it by a scalar. And notice also that we are allowed to multiply by 0, so the vector 0, 0, 0 is part of the kernel. It's in the span of 0, 0, 1. So the kernel, if we want to think of it geometrically, is the z-axis. Okay, next exercise. What is the kernel of the linear transformation T of x equals a times x from R5 to R4, where a is given here? This is a massive matrix, and to solve such a problem is going to take quite a bit of work. More work for sure than to figure out the image. This is the room you have. For convenience, I did it on a separate page because, as you can see, it is quite long. It's split into 4 steps, A, B, C, and D. Let's look at part A. So we are looking for vectors such that A times that vector we are looking for is equal to 0. So A times x1, x2, x3, x4, x5 equals 0. And that 0 has only 4 components. The output would be a 4-dimensional vector. So if you put this into your TI-Nspire and you look for RREF, which is a shortcut that we will typically do for large matrices whose order is large, this is what you get in the end. So this means x plus 2y, or maybe there's too many, we don't have enough room for all these letters, so let's say x1 plus 2x2 plus 3x4 minus 4x5 equals 0, and x3 minus 4x4 plus 5x5 equals 0. Here we need a little equals 0. So what we realize is that we have a bunch of free variables. we are going to be able to choose whatever we want for x5 and x4, and it'll always be possible to find an x3 such that x3 minus 4x4 plus 5x5 equals 0. And likewise, in the line above, we see that x2 is also a free variable. Whatever we've chosen for x5 and x4 will force x3, but then we can choose x2 again, and that will force x1 to be something. So that means we can choose x2, x4, and x5. Let's give them name. x2 equals r, x4 equals s, and x5 equals t. So now, from the two equations above, we know that x3 is actually 4s minus 5t, and x1 equals negative 2r minus 3s plus 4t. So the vectors in the kernel have that shape. It's x1, x2, x3, x4, x5, where we have substituted the values in terms of r, s, and t. This vector, or this is all the vectors that are in the kernel, can be split in a very interesting way, where we put all the parts that have r, and then all the parts that have s, and all the parts that have t. So in terms of r, we would have a vector r times negative 2, 1, 0, 0, 0, plus, which of these have an s? This one, negative 3, this one 4, and this one 1, plus a term for the t, so 4, 0, negative 5, 0, 1. It's much easier to think about this, what we got here, by going backwards. We would just add, and this is the final result typically, but this time we do it the other way around, and there's an extremely valuable reason why we do that, and that is that we can see now that our kernel is actually made of all combinations you can come up with of vectors negative 2, 1, 0, 0, 0, negative 3, 0, 4, 1, 0, and 4, 0, negative 5, 0, 1. So these vectors, which did not appear originally in the matrix, unlike for the image, are essential vectors. They can help us make a very clear statement about what the kernel is. The kernel is the span of those three vectors. Don't be confused by that 3, it's the page number. So that is how you find the kernel. And that step here to reach here is it's the clever step. The kernel has properties that are very similar to the image. First of all, the 0 vector is in the kernel. Now again, when we talk about the kernel and the 0 vector, we're talking about the 0 vector here, whereas in the image, when we said that the 0 vector was part of the image, we were talking about, not this one, but about when we have actually calculated a times x, we get 0. That would be what we mean when we say that the image, the 0 vector is in the image. So here the 0 vector is in Rm, so it's in the original space. And that's easy to check. We just need to plug it in. Let's see what t of 0 is. And if we do t of 0, it's equal to a times 0, and that is obviously equal to 0. So given that this happens, we know that 0 is in the kernel. This 0 here and that 0 here may not have the same dimension. One is an m-dimensional vector, and this one is an n-dimensional vector. Secondly, if we know that v1 and v2 are in the kernel, then k1v1 plus k2v2 is also in the kernel. So linear combinations of v1 and v2, or the entire span of v1 and v2, is going to automatically be in the kernel. How do we do that? We know that t of v1 is 0 because that's given, it's in the kernel. We know that t of v2 is 0 because that's the definition of v2 being in the kernel. And so we can just use the properties that we saw in section 1.3 and 2.1 to find the answer. So T of K1V1 plus K2V2 is, we can split the addition, the sum here, the operation, and then we can split the scalar from the vector, and since we know this is 0 and that is 0, then the final answer is 0. Therefore, K1V1 plus K2V2 in the original space is in the kernel. To end this up, we have 3 theorems. Firstly, if we have a matrix whose order is n by m, then if m is greater than n, there are necessarily non-zero vectors in the kernel. How can we think about that? If m, which is the number of columns, is greater than the number of rows, there's necessarily going to be some free variables when we do RREF. Think of a row echelon form or reduced row echelon form. You will have some free variables in there. So that means there's going to be choices for us to choose some of the variables, and therefore there's going to be more than just one way to have ax equals 0. B is the contrapositive of A. So that means if the kernel of A is made up of only the 0 vector, then m is less than or equal to n. And finally, C, if we have an n by m matrix, the kernel of A is equal to the 0 vector only, if and only if the rank is m. And to think about that is, again, we absolutely do not want free variables if our goal is to have the kernel equal to 0. And the way to do that is to ensure that the rank of A is exactly equal to m. It does not matter what n is. It can be a lot larger than m, or it can be equal to n. It can be equal to m. What we need is that the rank is m. N cannot be less than m, obviously, or that would limit what the rank is. At the end here is a summary that is very condensed, but it's worth once in a while to stop and read these and see and convince ourselves that yes, each of these is equivalent to the other. So that's it. Thank you so much for listening to this second part about kernels.